You know ERC-20 token and ERC-721. You have probably used OpenZeppelin contracts. But what the token looks like on a privacy-first blockchain. Today, we are looking at OpenZeppelin's compact contracts, which are fungible and non-fungible tokens rebuilt for Midnight zero-knowledge architecture. I'm Idris Olubisi, developer educator at Midnight Foundation. OpenZeppelin has partnered with Midnight to bring their battle-tested contract patterns to the compact ecosystem. This means familiar token interfaces with privacy-preserving capability. In this video, I will walk you through both fungible and non-fungible token. We are going to look at how they work, what's different from Ethereum, and how to use them in your dApps. Before we dive deep into the code, let's understand what makes Midnight token different. On Ethereum, ERC-20 tokens are fully transparent. Every transfer, every balance, every approval, it's all public on-chain. On Midnight, we have a different paradigm. Smart contracts are written in compact, a TypeScript-like language that compiles to zero-knowledge circuits. This means token operation generates ZK proofs. The blockchain then verifies the proof without seeing the underlying data. The OpenZeppelin contract are still in alpha and is currently unshielded, which means balances and transfers are visible. But the architecture is designed for selective disclosure. The goal is to choose what to review, compliance when you need it, and then privacy when you don't. Let's start with the fungible token, the compact equivalent of ERC-20. There are a few important differences from ERC-20 token. The first thing is that the token size is UINT 128 and not UINT 256, which is still a massive number, but something to be aware of. Secondly, no events. Compact does not support events yet, so you won't get transfer and approval events like in Solidity. And then finally, contract-to-contract calls aren't fully supported yet, but the module is designed in a way that it restricts transfers to contract addresses to prevent tokens getting locked. This is what it looks like in code. You have balances, you have allowances, you have the total supply, then you have the token name, the token symbol, and then the decimals. If you take a closer look, you notice the ETher type, which has the ZSwap coin public key, and then the contract address. This allows addresses to either be user public keys or contract addresses. The sealed keyword means name, symbol, and the decimals are set once during initialization and can't change. To set up your fungible token, you would need the initialize method, which will take in the name, the symbol, and the decimal. The important thing to note is that the disclose function is the key here. It explicitly reveals values that will be stored on-chain. In compact, you must acknowledge when data becomes public. For the transfer circuit code, let's take a look at the core operation. You have the transfer function where you could specify the to address and also the value. If you notice the safety check here in the code, the transfers to contract addresses are blocked because contract can't currently receive tokens safely. If you need to experiment with contract transfers, there is a function called _unsafe transfer, but you have to use that carefully. So because tokens sent to contracts may be unrecoverable. Let's talk about allowances. Allowances work like ERC-20 token that you are all familiar with. Here we have the approve function, which takes in the contract address and then the value. The own public key function returns the caller's public key, which is similar to the message of sender in Solidity. But then how does mint and burn works? Minting and burning go through the internal update function. So there's the _mint function where you can specify the account and then you can then specify the value that you want to mint. The update function handles all balance changes. So when minting, from is the 0 address, then when burning, to is the 0 address. So everything flows through one function for consistent accounting. Now, let's take a look at the non-fungible token, the ERC-721 equivalent. Same limitations apply, where you have the UINT 128 token IDs, no event, and restricted contract transfers. But there is one notable addition here, the URI storage. If you take a look at this code on the screen, we have the token URIs, which is specified to a map. And then we have the token URI function itself that takes in the token ID. And then we look up the token ID from the token URIs. Then we return the matching token ID from the token URIs. Since Compact does not support string concatenation, you can't do typical base URI plus token ID pattern. Instead, each token can have its own full URI stored directly. Let's take a look at ownership and approval states in ERC-721. The ownership model mirrors exactly what ERC-721 looks like today. We have the owners, you have the balances, you have the token approvals, you have the operator approvals. So, which means you have access to per token ownership, balance counts, individual token approvals, and the operator approvals for managing all tokens. But then for transfers, it requires authorization check. We have the transfer from function that takes in the from account and then the to address and then also the token ID. The internal update function handles the actual transfer, checking that the caller is either the owner approved for specific token or maybe approved as an operator. There is also a multi-token module, which is inspired by the ERC-1155. This lets you manage multiple token types in a single contract. Think of it like game items where you have different weapons, armor, and consumables, each with its own ID and supply. In the code here, we can see the balance mapping is now two-dimensional, where we have the token ID to account to the actual balance. As it stands today, no batch operation due to lack of dynamic array in Compact, but you will need to call mint, burn, or transfer individually for each token type. But wait, let me put this OpenZeppelin contract in context within Midnight's broader token architecture. Midnight supports 4 token types across 2 dimensions, where they are live or either private. On the vertical axis, you have ledger tokens, which live directly on the blockchain as ETXOs, and then contract tokens, which are managed by smart contracts like the ones we have been discussing. And then on the horizontal axis, you have the unshielded token, where balances and transfers are transparent and shielded tokens are private. The OpenZeppelin fungible token and non-fungible token modules that we covered today are unshielded token contracts. They are programmable ERC-20 and ERC-721 style token with custom logic, but balances and transfers are currently visible on-chain. But then, what about shielded token contracts? This is where it gets really interesting. A shielded token contract would be a programmable token like ERC-20 token, but with a privacy guarantee where balances are hidden, transfers are private, and also custom logic are enforced. But it's important to know that there's a caveat here. Shielded contract tokens don't fully exist yet. The architecture is confirmed by the Midnight engineering team, but the implementation is still being developed. The key difference here is that token minted via Mint Shielded in Compact today are shielded ledger tokens, but they are private, freely transferable with no programmable logic behind minting. But then, shielded contract tokens would combine privacy with programmability, but the exact implementation is still being developed. So when you are building today, use this OpenZeppelin module for programmable unshielded tokens. For simple private transfers, you can use the native shielded ledger tokens and stay tuned for shielded contract token as that implementation develops. OpenZeppelin Compact contracts bring familiar token patterns to Midnight privacy first architecture. You have the fungible token for ERC-20 token style. Then we have non-fungible token for NFTs. And then finally, we have multi-tokens for multi-asset contracts. These are same interface you know, but built for zero knowledge education. If you want to check out the entire Compact code example, I'm going to link in the description the OpenZeppelin Compact contracts, the GitHub, and also the Midnight documentation that you can take a look at and continue building. If you have any question, please do well to drop it below. I'm happy to answer all your questions. See you next time.